Welcome back to our sessions on simplified chemistry. We are looking at making these chemistry topics to be very simple and to present them in a way that it is easy for students to understand and even to be able to tackle questions in the exams including KCSE. Today we look at a topic in Form 3, gas laws, and we start by looking at the conditions that affect the behavior of gases, and here we are talking about two conditions. These are temperature and pressure. If you look at temperature, the SI unit for temperature is Kelvin, and we also use degrees Celsius, and to convert between Kelvin and degrees Celsius, Kelvin is equal to whatever degrees Celsius you have, you add 273. So K is equal to degrees Celsius plus 273. The standard temperature is normally 0 degrees Celsius, which is the same as 273 Kelvin. Room temperature is normally 298 Kelvin or 25 degrees Celsius. Let us look at pressure. The SI unit for pressure is Pascal or PA, or newtons per meter squared, nm squared. Millimeters of mercury is also used, centimeters of mercury is also used, and atmospheres are also used. All these are used as also measures of pressure. So under standard pressure or atmospheric pressure is normally 1001,325 Pascal or 1001,325 newtons per meter squared. It is also equal to 760 millimeters of mercury or 76 centimeters of mercury, and also equal to 1 atmosphere. There are two laws that express the effect of two physical conditions on gases. Let us look at the first one, which is called Boyle's law. Boyle's law. This states that the volume of a fixed mass of gas is inversely proportional to the pressure at a constant temperature. This means that increase in volume decreases pressure at a constant temperature. So this is represented like I've put it in this presentation, and what it means is that increase in pressure decreases volume. If you double pressure, you have the volume. So in terms of formula representation, P1 V1 is equal to P2 V2. So P1 is the initial pressure, V1 is the initial volume, P2 is the final pressure, and V2 is the final volume. So in terms of graphical representation, it's always presented as I've put in the diagram that I'm presenting here. So a fixed mass of a gas at 102,300 Pascal pressure has a volume of 25 centimeter cubic. Calculate its volume if pressure is doubled. So P1 V1 is equal to P2 V2. In our case here, P1 is 102,300 and V1 is 25. Then our P2 will be 102,300 doubled, which is multiplied by 2. Then V2 is what we are looking for. So to find V2, you will multiply P1 by V1, which comes to 2,557,500. Then we have P2 V2 is 204,600 times V2. So to get V2, you divide the 2,557,500 with 204,600, and you'll find that V2 is 12.5 centimeter cubic. Another example, you are told to calculate the pressure that must be applied to a fixed mass of 100 centimeter cubic of oxygen for its volume to triple at 100,000 newtons meter squared. You find that our P1 here is 100,000 newtons meter squared. Our V1 is 100 centimeter cubic. Our P2 is what we are looking for. Our V2 is 300 centimeter cubic because we are tripling the volume. And when you do your calculations, you will find that our P2 will be 33,333.333 Newton meters squared. Let us do another one. 60 centimeter cubic weather balloon full of hydrogen at atmospheric pressure of 101,321 Pascal was released into the atmosphere. Will the balloon reach stratosphere where pressure is 90,000 Pascal? Let us do our calculations. You find that our P1 here is 101,325 Pascal. Then our V1 is 60 centimeter cubic. Our P2 is 90,000 Pascal. Now we are looking at our V2. So if you do your calculations, you will find that our V2 will be 67.55 centimeter cubic using the formula P1 V1 P2 V2. So expected volume is 67.55 centimeter cubic, which exceeds the balloon's capacity of 60 centimeter cubic. Remember, we are told that the capacity of the balloon is 60 centimeter cubic. Therefore, the balloon will burst because it will exceed, the volume will exceed its capacity, and therefore it will not reach the stratosphere. Now let us go to the second law that determines or that explains the behavior of the physical conditions on gases, and this is called Chau's law. The law states that the volume of a fixed mass of a gas is directly proportional to the absolute temperature at a constant or fixed pressure. So this means that the more the volume, the more the temperature, the more the volume, because it is a direct proportion relationship. So in terms of formula, it is V1 over T1 over V is equal to V2 over T2. And remember that temperature is always represented in kelvins. So in these kind of questions, remember always to convert temperature from degrees Celsius to Kelvin. So graphical representation is as I'm displaying here on the screen. The volume of a gas decreases with the decrease in temperature until it reaches 0 Kelvin, until temperature reaches 0 Kelvin or negative 273 degrees Celsius. So the volume of the gas will keep decreasing with the decrease in temperature until the temperature is 0 Kelvin, which is called this temperature is called absolute zero. This point is called absolute zero. And this time now the gas does not exist. The gas cannot exist after 0 Kelvin. The gas cannot exist, and now it becomes a liquid. So this is what I'm presenting there in the graph. And now let us look at example calculations. 500 centimeter cubic of carbon 4 oxide at 0 degrees Celsius was transferred into a cylinder at negative 4 degrees Celsius. If the capacity of the cylinder is 450 centimeter cubic, explain what happens. These are the kind of questions you will find. You will be told to explain what happens. So what you do your calculations, and as we are saying, the formula here is V1 over T1 is equal to V2 over T2. In our question here, our V1 is 500 centimeter cubic at the temperature of 0, which now if you convert to Kelvin, you add to 73, and our V2 is what we are looking for. That's what we don't have. And then our T2 is negative 4 degrees Celsius, which you add to 73. So if you use the formula V1 over T1 is equal to V2 over T2, and you do your calculations as I'm displaying there, you'll find that the volume 2 will be 492.67374 centimeter cubic. So you'll find that with the capacity of the cylinder being 450 centimeter cubic, then the remainder of 42.674 centimeter cubic of the gas will not fit into the cylinder. Now let us look at another example. A mechanic was filling a deflated tire with air in his closed garage using a hand pump. The capacity of the tire was 40,000 centimeter cubic at room temperature. He rolled the tire into the car outside. The temperature outside was 30 degrees Celsius. Explain what happens. This is what happens. What you do, you calculate. You use our formula V1 T over T1 is equal to V2 over T2. And in our case, our V1 is 40,000 centimeter cubic, while our T1 is the room temperature, which is 25 degrees Celsius. Then our V2, that's what we are looking for, while our T2 is 30 degrees centigrade plus 273, because you need to convert to Kelvin. So when you do your calculation with our formula, you find that the new volume will be 40,671.1409 centimeter cubic. What does that mean? We are told that the capacity of the tire is 40,000. So what will happen to the tire when you put more than its capacity? It will just burst. So what happened is that the tire burst. Let's look at another example. A hydrogen gas balloon with 80 centimeter cubic was released from a research station at room temperature. If the temperature of the highest point it rose is negative 30 degrees Celsius, explain what happened. Same way here. You use our formula V1 over T1 is equal to V2 over T2. Here our V1 is 80 centimeter cubic, and our T1 is the room temperature, which is 25 degrees Celsius. You convert to Kelvin by adding 273, and then what you are looking for is V2. Our T2 here is negative 30 degrees Celsius, which you add to 73 to convert to Kelvin. If you calculate, you get that our V2 will be 65.2349 centimeter cubic. So the capacity of the balloon, as we were told, is 80 centimeter cubic, which is more than the new volume of 65.2349 centimeter cubic. So everything remains okay, and the balloon remains intact. Let us look at another topic here on gases, diffusion. What is diffusion of a gas? This is a movement of molecules of a gas from a region of high concentration to a region of low concentration. The rate of diffusion depends on density. So density is the weight. And the less dense a gas is, the higher the rate of diffusion. Density is also dependent on molar mass. So the higher the molar mass, the higher the density, and hence the lower the rate of diffusion. An example, carbon 4 oxide has a molar mass of 44 grams, while nitrogen has a molar mass of 28 grams. Therefore, nitrogen will diffuse faster than carbon 4 oxide. So let us look at another example, diffusion of ammonia and hydrogen chloride. We compare the two using an experiment here, where we are placing a grass or cotton wool soaked in ammonia at one end of a glass tube, and another cotton wool soaked in hydrochloric acid in the other end of the glass tube, and then we leave the gas to move inside the tube from both ends. So you'll find that there will be formation of a white disc or a ring, which is nearer to hydrogen chloride gas or nearer to the hydrochloric acid as compared to the distance to the ammonia solutions. So explanation, you find that ammonia has a molar mass of 17 grams, while hydrogen chloride has a molar mass of 36 0.5 grams. So it is more dense, the hydrogen chloride, as compared to ammonia, and therefore the white disk of ammonia chloride will appear near it, as it will be slow in diffusion. Because it is slow, so ammonia will come a further distance, as compared to to the hydrogen chloride, because hydrogen chloride is heavier than ammonia, and that is the reaction that happens to form the white ring, which is ammonium chloride. Let us look at Graham's law. This one is all about the diffusion. And what it says is that the rate of diffusion of a gas is inversely proportional to the square root of its density at a constant temperature and pressure. So, as it's being represented here, you'll find that the rate of diffusion is inversely proportional to the root of its density or its mass. So for two gases, if you had to do calculations involving two gases, you find the rate 1 divided by rate 2 is equal to square root of mass of 2 divided by square root of mass of 1. So since rate is inverse of time, the higher the rate, the less the time. So T1 divided by T2 is equal to square root of M1 divided by square root of M2. Let us look at example calculations. 1. It takes 30 seconds for 100 centimeter cubic of carbon 4 oxide to diffuse across a porous plate. How long will it take for 150 centimeter of nitrogen 4 oxide to diffuse across the same plate under the same conditions of temperature and pressure? And you are given there the masses: carbon is 12, nitrogen is 14, and oxygen is 16. So how do you go about that question? There are two methods. One method is you look at the molar mass of course you must start by looking at the molar mass of carbon 4 oxide, which if you calculate is 44. The molar mass of nitrogen oxide is 46. Now you are told that 100 centimeter cubic of carbon 4 oxide takes 30 seconds. And here we are dealing with 150 centimeter cubic of nitrogen oxide gas. So it is also good to look at the time it will take for an equivalent, which is 150 centimeter cubic of carbon 4 oxide to diffuse in the plate. So after you have now the time it will take 100 centimeter cubic. So you calculate now the time it will take 150 centimeter cubic of carbon 4 oxide, which you find that it will be 45 seconds. So now we apply our formula. The T1 over T2 is equal to square root of M1 over square root of M2. So we find that 45 seconds divided by T2, which is what we are looking for, is equal to square root of 44 over square root of 46, which now gives you, if you calculate, you will find that time that will be taken for nitrogen oxide to diffuse will be 46.0114 seconds. You can use another method whereby you consider now the 100 centimeter cubic of carbon 4 dioxide taking 30 seconds. You calculate for 1 centimeter cubic, and you get that the 1 centimeter cubic will take 3.3333 centimeters cubic per second. So this rate of the first gas divided by the rate of the second gas is equal to molar mass of the second gas divided by molar mass of the first gas. So this means that 3.333 divided by rate of R2, let us call it R2, is equal to the square root of 46 divided by the square root of 44. If you complete the calculation, you find that the rate for nitrogen oxide will be 3.2601 centimeter cubic, which now you can divide the 150 centimeter cubic that we've been asked about with the rate, and you find that it will take 46.0109 seconds. Let us look at another example. 25 centimeter cubic of carbon 2 oxide diffuses across a porous plate in 25 seconds. How long will it take 75 centimeter cubic of carbon 4 oxide to diffuse across the same porous plate under same conditions of temperature and pressure? And you have the masses of carbon and oxygen given there. So using our method 1, you find that the 25 centimeter cubic of carbon 2 oxide will take 25 seconds. So if you use an equivalent volume like what we have been given for carbon 4 oxide, you find that for carbon 2 oxide the 75 centimeter cubic will take 75 seconds. So now you can use TCO2 or T1 over T2 is equal to the square root of gas 1 over square root of molar mass of gas 2. So if you calculate, you find that it will take the carbon 4 oxide 94.0175 seconds to diffuse. So if you use method 2, you calculate the rate, and here what you do, the 25 centimeter cubic of carbon 4 oxide is taking 25 seconds. So 1 centimeter cubic of this, the same carbon 4 oxide, will take 1.0 centimeter cubics per second. This is the rate. So now you can use the rate. You say rate of CO2 divided by rate of carbon rate of carbon 4 oxide divided by rate of carbon 2 oxide is equal to molar mass of carbon 2 oxide divided by molar mass, that the square roots of the molar masses. You divide the one of carbon 2 oxide with that one of carbon 4 oxide, and if you do your calculations, you'll find that the rate of diffusion of carbon 4 oxide will be 0.7977. So now with that, you can divide the 75 centimeter cubic with the the rate, and you find that it will take 94.0203 seconds to have the carbon 4 oxide diffused through the plate. So with those, I think we've come to the end of the areas that needs to be covered in the gas laws topic, and those are the kind of questions that you'll always find in your exams. Let us just for you to have a feel of the questions, let's look at what has been brought in KCSE of late in this topic. You find in 2019 paper 1 there was a question of 140 or question 26, 140 centimeter cubic of nitrogen gas diffuses through a membrane in 70 seconds. How long will it take 200 centimeter cubic of carbon 4 oxide gas to diffuse through the same membrane under the same condition of temperature and pressure? You just calculate like we have done in the questions that we have tackled in our examples. In 2021 paper 1 there was a similar question. A volume of sulfur 4 oxide gas diffused from an apparatus in 96 seconds. Calculate the time taken by the equal volume of carbon 4 oxide to diffuse under the same conditions. You just use the same knowledge like we have discussed. The rate of diffusion of neon was found to be 1.4 times faster than that of an equal volume of gas X at room temperature. Determine the relative formula mass of gas X. That you can also be able to calculate. So another question was in 2022 paper 1 that said it takes 45 seconds for nitrogen 4 oxide gas to effuse through an opening. Calculate how long it will take for an equal volume of chlorine gas to effuse through the same opening. A simple question if you follow what we have done in our examples. We've come to the end of the topic of gas laws, and it's my trust that we've made it simple, and now it will be possible even to tackle all the questions that you come across in this topic. Thank you very much. We meet the next time when we look at another topic.